we did something with the equation already, so you have some concrete idea. But let's try to get the theory right. Okay. So if you have a line that isn't passing through the origin, like look like that. Okay. Okay. How can we express it as like a vector space or something related to a vector space? So the idea is like we take one point inside that line, okay, and translate the line based on that point, okay. So this point is a vector, and if we subtract this point from everyone, okay, so this point is W and this is a set V. If I subtract W from V, W will go to 0. Okay, so W will move to 0, but all the other points will move as well, right? And you end up with this set, and this set will look like a typical vector space now. Okay, so it's like you have a line and you subtract it with any point inside it. If you subtract a line with any point inside the line will move to 0, because that point will move to 0 and everyone inside the line will move along with it. Okay, and then you have the new line. Okay, and this line pass through the origin. Okay, and you can represent this as whatever you like. It looks like a vector space now, right? You can express it as a solution to a set of linear equations, homogeneous linear equation, or you can look at it as a span. Okay, so you get a vector space. If you translate it back, it passes through A, right? So you have this set. So the set will look like a set of vectors inside a vector space with some addition. So the vector A here, this vector A, will translate everyone. Okay, we move everyone at the same displacement. Okay, so everyone move at the same with the same displacement. So the whole line shifts as a whole. Okay. Okay. So is it a vector space? Typically, it's not, but we usually write it this way, and we call it an affine space. Okay. An affine space is basically a vector space after the shift step. Okay. So there's something called affine combination, but I'll skip. Okay. Now, so what we did previously is like we have a homogeneous linear system, and we solve for the null space of this system. Okay. So this is like metric A. We can take this as metric A, and then this is like the null space of A, right? Now, we have another system where it is non-homogeneous. How can we express the solution for this? Okay. So also, how can we talk about the system where it has many solutions? Okay. First thing we refer to this as non-homogeneous system. Okay. Now, if we have two solutions, okay. So this is the non-homogeneous case. Okay. Suppose we have two solutions of this. Okay. Suppose we have more than one solution. Let's say we have x1 and x2. They are both solution of this linear system, non-homogeneous linear system, and they are not equal. Okay. So there's both solutions. So it means like, so let me rewrite the whole thing as in the metric form. Okay. So a1 up to am is a vectors. So you know that this is a solution and this is also a solution. So this system is written as ax equals b. Okay. So if x1 is a solution, so we know that ax1 equals b, and also ax2 is a solution, so I know that ax2 also equals b. Okay, so they're both solutions to ax equals b. Okay, so we know that this is true and this is also true. Now, if I subtract both solutions, what does it look like? Okay, so I have solution x1 and x2. If I subtract it, I get, it's a vector, right? So I can subtract it. Okay, so what is this vector? Okay, what is this vector? So let's see. So if I multiply these vectors, so this is the vector that I'm interested in. So if I multiply it with A, so when you have a matrix multiplication, you can decompose it. You can write it this way. So it'll be ax1 minus ax2, right? Okay. And what is ax1? x1 is the solution of this ax equals b, right? So ax1 is b. And what is ax2? b. If you subtract b and with b, you get, so you get b minus b, you get 0. So what is it? So what is this guy? What is this vector? So if you're gonna take this note, let me write it in the typical way. I'm writing backward, so it's gonna be equal to x1 minus ax2, but they are both solutions of the non-homogeneous case, right? So you get b, you get 0. So I know that a times this vector is 0, so this vector, you have two vectors, right? And you subtract it, you get another vector. And you know that this vector, after multiplying with a, is 0. So this vector is, what is this vector? It's a solution of which system? So this vector is a solution of this homogeneous. This is not homogeneous. Okay, so if you take, okay, so the punchline is, if you take two solutions of the non-homogeneous case, okay, you have non-homogeneous linear system. If you take two solutions and you subtract one, you subtract them, right? The result will be the solution of the homogeneous system. Okay, pictorially, what does it look like? Look like this. So if you look at the non-homogeneous case and look at that in 2 dimensions, so the solution may look like a line like that. Okay, and I say that if you just take two of them and you subtract one of another, okay, what you get is like the result will be inside this line. You take this, subtract with that, so you get like this point, right? If you take any two of them, subtract them, the solution will lie inside this line. Okay, so the difference between two solutions of the non-homogeneous system will be the solution of the homogeneous system. Okay, so okay, so this is how we get the affine space. You see why? So this is the explanation. If you take two solutions and you subtract, then you have that this difference of the vector is solution to the homogeneous system. Okay. So this is the explanation. So on the other hand, so if W is a set of the solution of non-homogeneous case, if you take two of them, you subtract, then you get to the vector space. But if you just take one of them, like U, then you can express the solution of the non-homogeneous case as the solution of the homogeneous case. So this is the solution for non-homogeneous, but this is the solution for homogeneous case. It's homogeneous because they are all zero, right? But the solution for non-homogeneous is like you take one solution of the non-homogeneous case and then you can shift it using any solution of the homogeneous system. And we see that the solution is an affine space. Okay, so the solution of the linear system, if it's not empty, it's going to be an affine space. And this is it, and that's what we would learn about affine space. Okay, so this should summarize things. So if you have the homogeneous system, the solution will be a vector space. But if you have non-homogeneous, it's going to be an affine space. But you can think of it as the affine space. We have two components. One is the vector space from the homogeneous version of the system plus some solution of the non-homogeneous case. So let's wrap up with the exercise that you have just done. So here, the first two problems. So look at, please take a look. Okay. So what you did first here, you find a null space of A, right? But the null space of A is a set of solutions to the homogeneous system of linear equation here. Okay. Now we have another system which is non-homogeneous. Okay, this one is non-homogeneous. Okay, why is it a non-homogeneous system? Okay, we call it non-homogeneous because the constant on the right hand side is non-zero. Okay, but how can we talk about the solution of this system? Okay, so the idea is like when you talked about the solution of the set of all possible solutions, we sometimes refer to that as complete set of solutions. Okay, we can come up with that by figuring out just one of them. Okay, figure out one of the solution, and then you can add the solution of the non-homogeneous case, and then you get all the solution. Okay. So the idea is like in this case you have this vector space. Here you find one solution, maybe it's this, and then you add it to this, and you get the set of all solutions like that. Okay. So the reason for that, there are many ways to think about it. Okay. So if this is W, and if you take vector X, vector Y inside the solution of the homogeneous solution, so we have if AW equals B, AW plus Y, it's going to be AW plus AY, but Y is a solution of the homogeneous, so it goes to 0, so you get the same thing. So if AW is B, then AW plus Y, it's going to be B as well, because Y, vector Y is in the null space of matrix A, right? It goes through A and it vanishes. Okay, and this space is referred to as the affine space. Okay, all right. So there will be one homework on this, so you can practice to see if you actually understand.